What was I going to do? Oops, I forgot to record. Well, hopefully that's all right. We're going to start into our first unit of physics here. Any questions on any of the introduction stuff before I start? If you're still having problems with the conversion, again, come see me and we'll take care of it. Any other questions? Are we good? All right, good. So let's share screen here. All right, so this is our first chapter. It's called Kinematics. And inside of kinematics, we're going to be looking at motion in one dimension first. So like I said, if you I'm sorry, there's my calculator. All right, so if you end up struggling with motion in one dimension, guess what our next part of this is? It's going to be motion in two dimensions. So it doesn't get easier, it actually gets harder, and I assume that you know this stuff from one-dimensional motion when we get into two-dimensional motion, okay? So let's go ahead and get started here. The first thing I'm going to talk about, again, I'm not asking you to like write and then define these terms. It's just so you understand, you know, when I use them and stuff like that. So in introduction to physics classes, what this is, the whole basic like first year is what we call mechanics, okay? And basically it's a study of motion, like energy, forces, one-dimensional motion, two-dimensional motion, circular motion, stuff like that. So that's the bulk of your introductory to physics classes, all right? Because it's introducing you to the topics, and it's really mechanics heavy, okay? Inside of mechanics, our first one is kinematics, and basically all it is how things move. In other words, we're going to be able to put numbers to describe the movement of objects. So instead of just saying, oh, that car is going pretty fast, we're going to say, oh, that car is traveling this fast at this time and has gone that far. So we'll be able to describe it very accurately with numbers and with our equations that we're going to learn. Okay? Any questions? No? Good. Let's roll. All right, so before we start getting into actual topics, what you're going to need to know for this class is what we call frames of reference, all right? Now, your frame of reference is going to determine certain things, and it is possible in this class to have different answers, but both be correct, okay? And the reason why is because you could have different frame of references. All right, so I got to stand up for this one. I don't know how good I can do this. I demo this in my class because I have a lot of room. All right, so I'm going to get up here, and hopefully you can still hear me. If you can't hear me when I stand up, let me know. Just send a chat. All right, so for example, frames of reference, right? Have all of you see this picture? You see the picture? Does everybody know what that is? That's like the moving sidewalk at the airport, right? You guys have seen that before? All right.
Yes.
All right. So I'm going to give two examples, and I want you to tell me which description is correct. So let me see how much I do this. All right, you can kind of see. So when I'm walking on the moving side, or when I'm walking normally, okay, and if on the sidewalk, and I'm looking down at the belt, right? I'm looking down at the moving sidewalk. It looks like I'm moving like at a normal pace, right? Like I'm going in my normal walking, right? So I'm here, I'm looking down. It looks like I'm walking normally. So now, if I do this, where I start walking and then I look up, all of a sudden I'm like flying past all the stores, right? All the, like the Annie Ann's pretzels, I'm flying past them. So I'm looking down and all of a sudden I look up and I'm like, you know, going by, okay? So what description of my velocity is accurate? My walking normal pace, or me going really, really fast?
Really fast?
Charlotte, what did you say?
Really, really fast?
Okay. Okay. I mean, I was going really, really fast, wasn't I? Anybody think anything else? Nobody thinks anything else. Nice. All right. If you're embarrassed to talk, you could just type it in the chat. You guys are no fun. All right, so I guess I'll just use Charlotte's answer. So yes, obviously, me walking really, really fast is correct. But is me walking at a normal speed correct? Does anybody think normal speed is correct? Normal walking speed. All right, nice. It's like talking to this thing right here. Okay. Well, I'll tell you this. Remember how I introduced this where two different people could have different answers and both be correct? So really what's happening here is those answers are correct compared to what the frame of reference was. Okay, if I set my frame of reference to be the moving sidewalk, then yes, my velocity is my normal, walking speed. Does that make sense to you guys?
Yes.
If I set my frame of reference to be a stationary observer, in other words, somebody working at one of the stores and they're watching me go by, they're going to observe me, in other words, with their frame of reference, as going by really, really fast. So it depends on what you set your frame of reference to be, what the answer is. Okay, so both answers are correct depending on your frame of reference. Now, I don't want you to be like, oh my God, like we're gonna have different answers. I can't even cheat off of somebody because I don't even know what frame of reference they have. It's not like okay, different numbers or something crazy like that. What it is you'll be drawing pictures off of the real life situations you're reading about. And then what you're going to be doing is you have to set, so think about one-dimensional motion, okay? I can go, yes, frame of reference is basically point of view. Yes, all right. So what was I saying? Oh, so one-dimensional motion, right? I want you to think about this. You can either go this way or that way. That's one dimension. Or you can go up or down. You can't do left and right and up and down. It's either or, left and right or up and down. That's one dimension, right? How do I tell numerically if I'm going that way or if I'm going that way? Any ideas on that? How do I tell if I'm going that way or that way using numbers? So I said we're going to be able to use numbers to describe motion, right? Well, if my velocity is that way, or my velocity is this way, I have to be able to tell the difference using numbers. Yeah, Morgan, you better know that. Good. Positive and negative. Very good. Yes. Good. So yes. So think about it. Just number one. One way has to be positive. One way has to be negative, right? So I could set this way to be positive and that way to be negative. And then one of you could set that way to be negative and that way to be positive. Does it matter? No, it doesn't matter because it's your frame of reference. Now, you have to label your variables correctly relative to your frame of reference. Does that make sense? So it's just how you're setting the problem, and then you fit the problem into your frame of reference, okay? So I have a question for you. Suppose you're riding on a passenger train that's traveling 80 kilometers per hour. Convert quickly. No, I'm just joking. That wasn't a funny joke. You guys probably aren't laughing, even though I can't see any of you. And you start walking 5 kilometers per hour in the same direction that the train is moving. To the people on the train, you're traveling 5 kilometers per hour. What do the people on the ground observe? I'll give you a second. When you think you know how fast the guy's walking, can you please type it in the chat? You could be queuing this. You could be like, oh, I need to read it again because I really didn't understand. And I'm going to queue it. Oh, it's traveling at 80. That's the train. I'm walking here. Okay. Okay. You're traveling 5. What do the people on the ground observe? Okay. All right. All right. Anybody think anything different between 5? Who else thinks 5? And who thinks anything else? If there's any other answers, go ahead, put it in there. Okay, I got another 5. Only 2 people. Okay, I got an 80. Okay. I got another 80, so I got 4 people total out of a class of like 21 answering. Luke said 85. I don't know where you got that from. Logan said 80. All right, how about this? How about AJ? Can you tell me why you picked 5?
Well, you're walking at 5 kilometers per hour in the same direction, and that's not as fast as the train, but to others, you're still like slower than the train.
Okay.
So,
Okay. I mean, it makes sense. You're walking at 5, right? So they should see you walking at 5. Okay. Okay. What about Charlotte? Why do you think they're at 80?
Because I'm imagining them like at the station watching the train leave, so it's hard to see kind of through the train while
Oh,
they're
okay, you
on.
can see them. Okay, look, new train. This train has all windows. This is one whole window. You can see. Look, this is me walking. Even though, wait, yeah, you can't see my bottom half, but you can see me walking.
Oh, well, I think it's just you still see the train moving really quickly, which takes up more of your point of view than just you walking on the train.
Okay. Okay. What about Kenny? You said 75. Explain that.
So since you're already walking at 5 kilometers an hour and the train is passing by at 80, it's like you deduct the 5 because you're already moving that direction at 5. So what you see is just the other part of the train speed.
Okay. Okay. I see what you're saying. Luke, why did you say 85?
Well, I think I read the question wrong.
You did? You didn't do it? That was a joke. Nobody thinks I'm funny. It's okay. So you just read it wrong? Because you're the one that got the right answer.
Oh. Well, in that case, I think I'm a genius.
Oh, whoa. You got to explain why you picked 85, though. I got to hear why.
Well, okay.
What's the genius?
Because relative to the ground,
Okay.
you are traveling 85 kilometers an hour.
I agree with that. But how'd you come up with that 85?
I added 5 to 80.
Why'd you add 5 to 80?
Because you're walking,
Right.
and then the trains, so the people on the train are going 80. So then, yeah.
Right. Where are you walking? You're walking on the train, right? So, yes. See, Luke, you knew what you were talking about, man. Don't sell yourself short. You just, if you have the right answer, I usually try to make it so you think you're wrong so you can explain it, right? Because if you just say out answers and just, I got it. And so stick with your guns, all right? And I like to hear like the thought process behind all the answers, all right? So good job. Yes, so to the frame of reference of somebody sitting on a bench as a train goes by, think about it. They're actually going to see you walking faster than the train. Okay? And that should make sense, right? Because if you start here at this point walking, the train is going to be moving, and we're observing this, right? You can see this drawing, right? We're going to be the stationary observer. As that train moves, if you are moving the same speed, you would stay at that point in the train, right? Does that make sense? If you were moving the same speed as a train, you would stay at that part because you'd be both going 80. But what happens? You move in the train forward, right? So to move forward in the train, you need to be traveling faster than that train. So to a stationary observer, in other words, us outside the train, when you somewhere down the road, so this is somewhere down the road, all right, you get right here. How'd that happen if you're moving the same speed or moving at 5? You're not. to an outside observer, you're moving at 85 kilometers. Now, again, which is correct, the 85 kilometers or the 5 kilometers? Well, it depends on our frame of reference. If our frame of reference is inside, it's 5. If it's a stationary observer, it's going to be 85. Because you're not going to be, so when I say he's walking at 85 kilometers per hour, it's not like he's like going to the bathroom. It's like, choo choo, like, oh, whoa, where'd that guy go? Like he's going 85 miles an hour on the train. No, it's because it inherits the train's velocity because of how you were observing. Does that make sense? You see the difference?
Wait, I have a quick question. So,
Yes, who's talking?
Annie.
Okay,
So
go ahead.
would it be like 85 for both of you? Like, let's say I'm like sitting down on a bench and the train is passing by and somebody's walking by them too. Would it be the same for the person walking and me sitting, or like difference?
So there's somebody walking by you.
No, like, okay, so the person walking, right?
Uh-huh.
They're walking and I'm the one sitting down looking at them. For me, they would be going 85. But for them, would they feel?
Where's the person walking on the train? I don't think,
Oh, I just confused myself. Never mind.
yeah, you confused me too. It's all right. So you're sitting on a bench, right? There's another person besides the person walking on the train, or you're just talking about the person on the train?
Like a person beside walking on the train.
Okay, so are you on the train or are you off the train?
Off the train.
Off the train. Then you see this guy in our question that's walking 5 kilometers per hour this way, right? He's walking this way because the train's moving this way. Then you see him go 80. His velocity is 85 compared to you. Now, you're talking about somebody else watching this and walking?
What if I was that guy walking down? I would be going 5, right?
What if
I was the guy walking the same way as the train?
Oh, okay. Well, you would see, what are you asking? You're asking how fast you would see yourself walking?
Uh-huh.
Well, it depends, right? That's the same as my example with the moving walkway. If you look at the train, and like the seats, if you look down at the train, it's going to look like you're walking 5 miles an hour. But if you look out the window, right? So you're walking and you look out the window, what are you going to see? All this crap going by really, really fast, because now to that frame of reference, you're going 85 miles an hour. So you ever see like people like okay, you might not because it's kind of like corny, but they like walk and they look outside and they're like, and it looks like they're running really, really fast. And you've seen that? All right, well, whatever. You guys are boring. All right, Annie, did that make sense?
Yeah.
Good. So that, if you're on the train, if you're the person on the train, it's just like my example with the moving walkway. Okay?
Got it.
All right, good. Oh, man. This is rough over Zoom. This is not fun. All right. So, didn't even come up with the answer? What is going on here? Oh, I guess I didn't even put the answer. All right. So, next thing we're talking about is, I think it's, distance versus displacement. Okay, distance versus displacement. Can anybody give me a definition of distance? Or just like an example.
How far you go.
How far you go. That is money, Vaughn, that's a perfect definition. What about displacement? Can anybody define, displacement?
Where you end up after the whole trip.
Okay, so can you say where you end up?
It's like the distance you travel minus where you end up. Like how far you went, but like you subtract how far you went and where you ended up.
You're right there, you're almost saying it. Yes, it's where you end up compared to where you started. So you can be subtracting where you started, right? Does that make sense?
Yep.
All right, so here's our definition. So distance versus displacement, okay? Displacement is where you ended up compared to where you started. So in other words, you're just comparing it to your starting point. Displacement is a vector. Who knows what a vector is? Who's seen what's that movie? Despicable Me. Anybody seen Despicable Me?
Yes.
All right. Well, what's the bad guy's name in it?
Vector.
Vector, right? The guy. Yeah. I'm bringing this up. You guys stay with me here. All right. So why does he name himself Vector? I mean, he tells you.
Because he's a cool guy now.
Nice. All right. I'm gonna mess up.
Is it a quantity having direction as well as magnitude, especially?
Yeah, we already got that in the chat. I'm trying to figure out how to say.
Okay. Dang it.
Hamaz. Is that say it right?
Hamza.
Hamza. Got it. Hamza. All right. Yeah, Hamza got it first. So he's like, oh, I commit crimes with magnitude and direction, right? Well, that's literally what a vector is. It has a magnitude, in other words, how much, and a direction, which is so important. This is the most important thing right here. Because this is important. It is a vector. It has a unit of direction. This is important. Okay? Because again, how did we say we're going to determine right or left in this chapter? Oh, with positive or negative. Okay? The units here, it's a length, right? Our displacement, where are you at from where you started, is a length. So it's going to be in meters. Okay? Any questions so far? We okay? All right, good. Keep rolling here. Okay, yeah, well, we'll get into this. This means displacement. Okay, we're going to get into that with my examples. All right, so if you remember, I guess it's on the screen. I was about to ask you what the triangle thing meant. So delta x, so displacement is going to be represented by this variable right here, delta x. So if you're reading a problem and you're like, oh, that's the displacement, you're going to write it as delta x equals this. And how we use it in this, so sometimes I use this, final and x initial, but in AP physics, they use it as x and x naught, right? This is going to be x, and that's going to be x naught. X is the final position, x naught is the initial position. Okay, so that's what Kenny was saying. You're going to take your final spot minus your initial spot, right? Kenny, that's what you're trying to say, right?
Yep.
All right, perfect. So that's our equation for delta x. All right, remember displacement is delta x, and you're going to have positive or negative because it has a unit of direction. Okay, any questions on displacement so far? So in little pictures here, you know, did it ever pull, hold on, did I miss distance?
Yes.
Where did that? What? What happened to my PowerPoint here? All right, well, I'll just tell you what this distance is. So distance, like you guys said, is just your total amount traveled. Total amount traveled. So let me do an example. I'm going to stand up and do an example for you. So let's say I start right here. I'm starting right here. I'm going to walk 5 meters this way. All right, I walk 5 meters. What is my distance traveled? Distance.
5 meters.
5 meters, right? What is my displacement right now?
Five meters.
Still 5 meters.
What are you missing?
Is it meters per second?
Always have?
What?
I said, can you guys hear me? I said, what does displacement always have, right? I walked 5 meters that way.
A unit of direction?
Right, so you can pick, is it positive or negative? I don't care. So you could just, what I wanted here is either a positive 5 or a negative 5. So you can say, oh, you walk positive 5 meters. Does that make sense? Because you need to know that this is a positive direction, that's the negative direction. If we to be that, all right? So 5 and 5. So what if I now walk back 5 meters? What's my distance traveled now?
10 kilometers.
10
meters.
10 meters, I agree. What's my displacement now?
0.
0, very good, okay? What if I do this? I walk 5 meters this way. What's my distance traveled?
15.
15. What's my displacement?
Positive 5.
Negative 5,
Negative
since
5.
the other side was positive.
Negative 5, very good, because if I set positive this way,
Oh, that was.
I ended up that way, this is negative, right? So I'm to the left, or on your screen, I think it's going to be the right, of where we started. Does that make sense? So if I set my initial way to be positive, which I did because we said it's positive 5, I came back to 0, and then I had to go negative 5. So do you see the difference between distance and displacement? Does that make sense to you?
Yeah.
And distance is a scalar. A scalar is just a number, okay? It's just a number. Are you supposed to be taking notes? So with these lectures, here's my advice to you, all right? If you're taking AP Physics, you're probably going to college, right? And in college, they don't check to see if you take notes. They don't care. They're not going to be like, hey, turn in your notebook. I'm not asking you to turn in your notebook. Don't care. All right? So you need to figure out what works for you, whether it's, you're going to write down everything, you're going to print out the PowerPoints, I'm going to make it available for you, and you can jot down notes. Because you can see, I don't really read from it. I do a lot of extra stuff. So it's kind of like just jotting down notes. You got to figure out what works for you. So, no, I'm not making you take notes, but this is what the class is about. So do with that what you may, I guess. All right? Good. So again, two more examples, right? The blue line here, well, I wouldn't recommend writing down word for word because, like I said, I'm not going to have you memorizing stuff, and you can always just pull this up. You can just print this PowerPoint out, or just, if you're just going to copy down the terms, you can just write it. But as per, just jot down, what I was talking about. And again, we're behind the 8 ball with this online stuff because, you're missing out an entire class every 2 weeks, and we're missing time every single day. So it's tough. I know. We got to move because, we are going to the AP test. That's why I would utilize what's called office hours and stuff like that. So distances here, the whole path, that's just a number because it doesn't matter what direction you're going, right? You're changing direction the entire time here. Doesn't matter, doesn't matter, doesn't matter. All right? This, you're going to go from here to here, straight line. I started here. I started here. I ended here. Okay? Done. Make sense? Everybody kind of understand distance versus displacement?
Yeah.
Okay, let's go on to this. Here's a question. So, what is the distance traveled? So this is a position is on the y-axis, right? So where are you at? Versus time graph. The black line represents how you travel, where you're at. So what is the distance traveled for the object in the graph below from 0 to 6 seconds? I'm going to give you a second and type your answer in the chat. What is the total distance traveled from 0 to 6 seconds? Everybody agree 12? That makes sense. If you don't get it, here we go. Ready? I'm starting at 0. When I get to here in 2 seconds, I've traveled 4 meters, right? when I get to here in another 4 seconds, I'm back to where I started, right? I'm back to my initial point, so I went another 4 meters. So 4 meters, and in 6 seconds, I travel down here, I go another 4 meters, right? So 4 plus 4 plus 4 is 12 meters. Everybody okay with that? Any questions on that? Remember, distance is just a number. No positive or negative, okay? There's the answer. Good, 12 meters. All right, read this one. What is the displacement of an object in the graph between 0 and 6 seconds? Think about that. Type your answer when you get it. Very good. -4, right? Does that make sense to everybody? So you go here, you go here. That's +4, right? You end up back to where you started, so the displacement here would be 0, but then you end up down here, which is -4 from where you started. You started here, you ended up down -4, so my delta x would be -4 meters. Make sense, everybody? Seems like everybody kind of got that concept. How we done? Oh, 240. Ooh, ooh. Yeah. All right, we're gonna just go on. All right. So average speed and instantaneous speed. So speed and velocity and stuff like that, like those are terms that you're kind of familiar with, right? You use them all the time, like, oh, what's the speed limit? And, you know, stuff like that. So you've used these terms. Now we're going to actually put like equations and definitions to them. So when we look at speed here, so speed is the distance traveled divided by the time it takes to do so. So remember, so speed is a scalar because distance is a scalar. So think about this. When you have your speed limit, or you know your speed in your car, when you turn the wheel, isn't your direction changing? And it doesn't like all of a sudden your speedometer go like negative and positive, right? So when you think about this, speed related to your car, it's just a number. It's how fast you're going, right? Okay, and this is a definition of average speed. Oops, I'm trying to draw here. Okay, that's a definition of average speed. So if you're talking, and that's like, you guys have, anybody have a car with the information center, and it's like, you know, your average miles per gallon and your, you know, like your instantaneous miles per gallon, but then you might have your average speed. Does anybody's car have that? No? Okay, you might not. Some cars have it, some cars don't. But it has like an average speed. And all that does is it takes how far you've gone on the odometer and just timed how long you've been driving. And it does this equation right here. So it's not like some like crazy thing like, oh man, it knows how fast I'm going. No, it just sees how many miles you traveled and how long you've been driving. And that gives you your average speed. Okay? Now, your instantaneous speed. So average speed is when we're looking at like a whole trip, right? We drive from here to Woodbridge High School. What was our average speed during that time? Well, we take the whole distance divided by the whole time, and that's our average speed for that entire trip. Instantaneous speed is if we're taking like a split-second look, like, okay, when you passed the Chick-fil-A, how fast are you going? Well, at that point, I was going exactly 45 miles an hour. So at that instant, what was your speed? Do you see the difference between average speed and instantaneous speed? All right, good. Again, like I said again, speed is a scalar and can only be positive or zero, because you're not going to have it negative because it's just a scalar. Scalars are always just positive or zero, okay? So if you look at this, right, I said distance over time is our definition, right? So again, what's our unit for distance? It's going to be meters. And what's our unit for time? It's going to be seconds, right? So our units for speed are meters per second. It's not like your car where it's miles per hour. All right, it's going to be meters per second here. Any questions on speed? You know what that is, right? We're all right? All right, good. Clear this. So again, this is just kind of a visual. I just literally wrote out these equations for you. All right, distance over time. Okay, when you're talking about average, you're looking at a large distance this whole entire time. As you can see, you even change direction here. It doesn't matter. You're using that whole entire distance. That's why it's always going to be positive. So that orange line is your large distance over your large time, and that gives you your average speed. If you're looking at instantaneous, you're going to look at a super small distance. Like, oh, how fast are you going when you pass Chick-fil-A? Well, I'm going to take the super small distance in front of Chick-fil-A, time it really quickly, and at that instant, that's how fast you're going. Okay, is everybody okay with that? I'm going to pause here for if you have questions on speed. Okay, good. Need to get through one more thing. Okay, well, yeah, answer this question. What is the average speed of the object in the graph below from 0 to 6 seconds? So what is the average speed? Go ahead, type an answer in when you get it. Very good, 2 meters per second. So again, I'll do it real quick. That's good. If you guys are getting this, that's good. So the total distance, which you already asked you said the distance was 12 meters. The time is 6 meters. So our speed is equal to 12 over 6, which is equal to 2 meters per second. Okay, very good. Good job. That's good. I know I'm going super fast right now, but I got to get at least this next slide in here. All right. That's just the answer. All right, so average velocity and instantaneous velocity. We are going to be working, even though we say speed a lot, we're always talking about velocity because we're always going to include distance, or I mean direction. I'm sorry, not distance, direction, all right? So when we say, oh, how fast are you going? Well, I was going positive 35 miles an hour or negative 35 miles an hour. That doesn't mean you're in reverse driving your car. It just means, oh, are you going this way or are you going that way? Because we have to determine which way they're going. So the definition of velocity now is displacement divided by time. So average velocity is going to look like this. Average velocity is equal to delta x over t. That's your equation right there. Okay? Now, when you're talking about average, it's the same thing. You're going to take a big thing. It's the same thing here. I'm not going to go through it. But we're actually going to work with instantaneous velocity a lot. Because you're going to say, oh, the car started out at rest. So it started initially at 0. So that's its instantaneous velocity at that point. And then, oh, what was its final velocity once it goes down the road? Oh, we're going to pick a point and calculate its instantaneous velocity at some point down the road. So with this, you're always going to be talking about velocity, instantaneous velocity. We don't really work with average velocity a lot here, okay? So the things to remember that this is a vector. So that means it's going to be positive or negative, and this just tells direction. Just tells direction, okay? Let's go next slide. That's literally what I just said. Answer this question. This will be the last thing for today. What is the average velocity of an object? So between 0 and 6 seconds. Remember, it's you're probably gonna get a weird number and not understand it, but trust your gut. If you know what displacement is, Tyler, good job. Good. Good. Okay, so let's look at this. So my velocity equals displacement, which I said from the first time was -4 over time, which was 6, right? So if you do that in your calculator, you're going to get -0.67 meters per second. Negative just means at this point right here, the average velocity was going to be heading towards the left if that was negative. It's just telling you direction. This is direction, okay? Any questions between distance and displacement?
Could you review displacement for this example again?
Yes, yes. So remember, for displacement, you don't even have to worry about what's going on. You don't even have to worry about what's going on there. Don't even look at that. You're starting at zero. You start at 0, so that's your initial position. You end at 6. This is your final position, right? So if our definition is final minus initial, if I ended up at -4 and I started at 0, that means my displacement is going to be -4. But I can always plug it in here. My final, this is final, is -4. My initial, I started at 0. And that's why I got the -4 meters as my displacement, which I can plug in there.
Wait, why is it the final -4?
Because you're going from 0 to 6 seconds. So at 6 seconds, where was I at? Oh, I was at -4 meters.
Oh, okay, because I thought it had something to do with 12 meters, like the way that it was.
Remember that 12 meters is distance. Velocity has to do with displacement. Does that make sense?
Okay, yeah.
Okay. All right. I'll hang if you have any more questions. I know class is over. I will be sending out an announcement in the next 10 minutes because it's going to be easier instead of me like going through the modules and pointing out stuff. I'm going to send out a announcement with what's due for your asynchronous work. Does that make sense? You know what I'm talking about when I'm talking about asynchronous? It's like the Monday, what you need to do. All right. If you have a question, please respond on the announcement because I'm sure somebody else might have the same question. That way it cuts down on the emails I have to answer because I just answer the questions and then everybody can see it. Does that make sense?
Yep.
All right. So I'm going to hang if you have questions. If you don't have any questions, you can leave and then just look for that announcement and make sure you're turning in your work. This is easy stuff, man. You need the free points because I can tell you the tests are hard, and it's just because we're getting you ready for the AP test. So you should have like these points are easy. Like the graphing assignment, I just went over some of it, and it should be easy points. Okay, does that make sense? Like I want all of you to have good grades, but just take care of business, and then you will, that way you have a little buffer in case something happens with the test. So again, I'll hang if you don't got anything. See you next time and have a good weekend. Okay.
Thank you.
Bye, Mr. Thomas.
All right. We'll see you. Have a good weekend.
All right, thank you, Mr. Thomas.
Yep.
I have one more question. I'm so sorry.
No. Hey, it's okay. It's okay. Go ahead.
What exactly will be covered on the quiz on Monday again?
I'm actually going to type that exactly in the announcement. I'm going to give you every single question. Not give you the question, but list what you need to know.
Okay, that was just it.
Okay. Yeah, no worries. Yeah, I'll make sure you have that. That way there won't be any confusion.
All right, have a good day.
Thank you too.
Mr. Thomas, about
Yes.
the graph homework that we did, I'm confused about the I forgot. Hold on. The mx plus b thing.
Okay, so let me share a screen with you real quick. So let me see. So mx plus b. You've seen this before, right?
Yes.
Okay, so remember that this is slope. So did you calculate the slope of your best fit line?
Yes, it was 2.5.
Ooh, are you
I
sure?
don't know how I got that.
I would double check that. That doesn't sound right to me.
Because for the slope,
I'll give you a hint for slope. So slope is rise over run. So what you do is you pick so if this is your line, as best you can, like if you print it out and use graph paper, it's gonna be a lot easier. But like I freehanded it, so I kind of had to estimate too. You're gonna pick 2 points on that line at somewhere, right? And this is gonna be x1, y1, and this is gonna be x2, y2, right? Does that make sense to you so far?
yes.
You're just picking 2 random points. I had to estimate on mine because I didn't use graph paper. And then if you're not using graph paper, you just kind of estimate. I mean, you're going to get close enough for it to be good, okay? So you get these points, so then you're going to use it to plug into this equation. So your rise is you're going to do y2 minus, hold on, I'm running into this stupid thing. Sorry, hold on. Y2 minus y1, because that's the change in your rise, right?
Mm-hmm.
And then you do x2 minus x1, and that's going to give you your slope.
Yeah, I think it was that I got for some reason it was just hard to calculate because I didn't have graph paper. That's why.
That's fine.
I got a weird number.
I don't know if you can see mine, but like I kind of just estimated. Like I was like, I'm gonna go right here, or I knew this was like I just went where I had something on the x and kind of went up and estimated where it would be on the y. So I knew I was getting the x right. I was like, all right, for sure I know the x is supposed to be here. I got to estimate it on the y, and that's going to be my first point.
Okay.
So just try doing that. So then once you calculate the slope, it goes here. And then my line, this is your vertical intercept. So vertical intercept, right? So my line goes like almost through 0 because we have a point that's 0, 0, right? The first point is 0, 0.
Mm-hmm.
There is a point like right there. So my line literally looks like that. So I'm like, it's close enough to 0, so I'm just going to get rid of it. Okay? Is that your question or no?
So we get rid of it if it's just close to 0?
Yeah, if it's 0, just put it at 0. And if you add 0 to anything, it's just this, right? Now,
okay.
if your line looks something like this, right, it obviously has a vertical intercept, so whatever this was would go there.
Oh, okay.
Okay?
And so so then all would be left would be y equals the slope x, right? Then
Right.
what would
Isn't that the problem? Then you ask for, write the equation for the line, that's it.
Oh, so that's just the answer, y equals something, the slope x.
That's the equation for the line, yep.
Oh, okay, thank you so much. I was so confused.
Yeah, no worries. And then for number 8, where you see use the equation, determine what the potential energy would be at 30 meters. So potential energy in our equation is on the y-axis, right? So that's y. Does that make sense?
Oh, okay, so I just put in the number there and then solve for x?
No. You're
No?
looking for y because it wants you to find potential energy. You would put 30 in for x because x is the height. Remember the x-axis was height and this was potential energy?
Mm-hmm.
So potential energy is y and height is x. So it gives you a height, so you put 30 in for x and then solve for y, and y is your potential energy.
Oh, okay. Okay.
Make sense?
Yes, thank you so much.
Alrighty.
Bye. See you later.
Yep, have a good day.